So I've got a lot of stuff here on top of the hour, as they say in the radio stations. First off, Teresa, I have an answer to your question. Okay. It's still messing it up. Okay. Well, if you have this problem, everyone else is. So a lot of you use SAS University Edition. It recently wants to update itself once you log in, and it changed the name of the default place where your stuff is, apparently, in the process. So I opened up a file that I had made, and so do you guys know how to make shortcuts within your VirtualBox to where your stuff is? So I had done that inside, so here's my VirtualBox thingy, and if I go to, I think it's maybe settings, I'm trying to remember how to do this, it's been so long, shared folders, yeah. And then you can, it wants you to create a specific spot called My Folders as its default, but that's not where all my stuff is. So I created another one that is just the link directly to my Dropbox. And so previously I had SAS files, syntax files, excuse me, that referred to something that looked like this. Let me take this off of here. So it was slash is going the wrong way, according to my Windows here. Folders, then My Shortcuts, and then the name of the shortcut was called Dropbox, and that wasn't working. So I tried to figure out where it went by navigating to it, and I noticed that now under folder shortcuts it's SF_Dropbox. For no apparent reason, it just decided to change it. So sure enough, I added the SF_ to the shortcut I had previously named, and it worked. So just as a heads up, you may have to add SF_ to the front of your things for no apparent reason. I also found a trick here. I navigated to where the file that I was using was, and I was like, okay, where does it think this folder is on my drive? Because it's like, there is no place called folders, right? I mean, this is not an actual path. And so I right-clicked on the file, and I saw that I had an option for properties. And under properties, it tells you what it thinks the link is called. And that's where I figured out that I had to add this SF thing right here. So that's what I would do, is use the Explorer tab to navigate to where your stuff is and then figure out what it thinks it's called in there. And that should hopefully get you to the right place. If your homework is due in 2 hours and I'm not answering emails perhaps, and you're like, what do I do? You should be able to remote desktop into this room also. So that should be your backup plan. Each of you has an IP address assigned to your name in Blackboard as an announcement so that you can use these machines after hours as well. So just a heads up on that. Any other technical issues while I'm on the topic? No? Okay. Another thing here, homework 4 is up, and there is a catch to the very, very first question that I wanted to make sure I pointed out to you. So way back last semester, the very first set of examples that we had, I had printed this table called iteration history. And this is where you're used to getting your -2 log likelihood with 3 digits after the decimal, right? When you run your very first model for your homework 4, it's an empty model with E only, no random effects or residual structures of any kind. This table doesn't print because it actually didn't need to iterate. So what you'll need to do is run the next model where you've added a random intercept. You'll get this table where the last entry is for the current model with the random intercept. The previous entry is what you'll use for the E-only model instead. So this is the starting point for the iteration process. It doesn't need to iterate if it doesn't have anything defined. If it has a random intercept defined, it only needs to iterate once. So just to reiterate, the first one will be for the E-only model. The second one will be for the final model with the random intercept. And from that point forward, that table should print. And I also found out that some of my videos are broken for reasons that are also unclear. The audio went out on some of them, and some of them don't have any audio. Thank you, Ejin, for telling me about that. It's the YouTube. I don't know. I think it has to do with whether or not this computer loses connection to the internet and things go haywire. So I apologize if there are technical difficulties, but unfortunately that copy of the video is the only one that I have. So there's no like better copy someplace that I can use to fix it. So sorry about that. Okay, there's that. I think I can go ahead and kill University Edition here. Power off the machine, please. And let's talk quizzes. I want to leave this site. And I want to make that go away. There we go. All right, so you have a quiz for today, yes? Shall we go over it per our usual? I wrote more than usual for my answers because I wanted to make sure that this stuff was clear. We're going to go back over this today in the context of cluster data, but it's the same set of rules. So I'm trying to use generic terms here, level 1 and level 2, so that it applies to any kind of research design that's 2-level. Up to this point, level 2 has always been person and level 1 has always been time. But in our current example and in moving forward, the levels are going to change based on the design of the study. So for now, you can think about these as time and person, but they also apply to person within group. So question 1, when will a level 2 random intercept variance be reduced by a new fixed effect? What did you say? A level 2 predictor, more specific, what kind of effect of a level 2 predictor? Looking for one more adjective in front of effect. Main effect, yes. A main effect of a level 2 predictor or an interaction among level 2 predictors. Those reduce level 2 random intercept variance. Very good. Level 2 intercept variance will also be reduced inaccurately to the extent that you have a smushed effect in your model. The between level 2 part of the level 1 smushed effect will also reduce the level 2 random intercept variance. And we saw that in our example, somehow a student level predictor was able to account for school level variance. The only way that happens is if there's school level variance in the student level predictor as well. And then when will the opposite happen? When will the level 2 random intercept variance be increased after adding a new fixed effect instead? I'll let there be awkward silence. I'm down with that. Let's see who blinks first. When will the level 2 random intercept variance go up after adding a new fixed effect? When the new fixed effect is, who's talking? That, I heard it. Who's me? Okay, sorry. I just hear shy voices in the back, and I'm not sure where it's coming from. When the new level 1 fixed, it's the new level 1 fixed effect, right? But a level 1 fixed effect of what kind of predictor specifically? There's a certain characteristic of it that makes this happen. And I don't know that I've emphasized this point before, but it's worth emphasizing now because we have an alternative possibility. Level 1 fixed effect where the level 1 predictor is exclusively level 1. Meaning that it has an interclass correlation of 0, that it's been person mean or group mean centered to remove all of its level 2 variation. Because in that case, it shouldn't affect the random intercept variance at all. But because it reduces the residual variance reduction then makes the random intercept variance go back up. And this will be more obvious in samples that have smaller numbers of level 1 units per level 2 unit, because the correction factor in this process is residual variance divided by the number of level 1 observations. So if you have a lot of level 1 observations, you won't see this happen very much. If you have very few, then you'll see a marked change in the random intercept variance going up anytime residual variance goes down due to a new pure level 1 predictor. Question? If it's not being broken down, then the level 1 predictor will be the thing that's reducing the level 2, but it's exactly right.
Okay.
Yeah.
And then I mentioned a few things and then for question 2, I just said it doesn't. So then you fix that as level 1 predictor that doesn't have level 2 variance.
Yeah. Yeah, you can say it that way too. Yeah. So if you have a level 1 predictor, let's do my friend Excel here rather than writing on the board here. You have our level 1 X that has been either grand mean centered or not centered at all, right? So it has both kinds of variance in it. So it has level 1 within variance and level 2 between variance. The level 1 within part should reduce the residual. It's not a formula. Can I do that? There. Should reduce, that's what I'm trying to say, Excel. And the level 2 between part will reduce the random intercept variance. Let me put the levels in front of here so we keep track of everything. So if you have a level 1 predictor that has both kinds of variance, the level 1 part of it will reduce the level 1 residual. The level 2 part of it will reduce the level 2 random intercept. Now this is what we refer to as the smushed effect, because only putting in one predictor for both of these things says that both of these things have to have the same fixed effect. If you instead take your level 1 predictor, and I'm just going to use the generic term here that it shows up in chapter 11, variable centered, meaning you've centered it at a person mean or a group mean, but the point being is that the thing you've centered it with is a column in your data set. It varies from case to case. Then it only has level 1 within variance, and it can only capture level 1 residual variance. Because level 1 residual variance went down, level 2 random intercept variance goes up. So you don't see that here because in reality it went both up and down, but the net is probably going to be down unless this model is really, really misspecified. So things then that reduce level 2 random intercept, let me add another column here. In addition, level 2 between effects, right? Level 2 random intercept variance is accounted for those. Does anything happen to residual if you add a level 2 between effect? Nope, it should stay the same, or very close to the same. Okay. Any that you want to hear again? Okay, let's keep going then. How do you know which variance component a cross-level interaction, an interaction between a level 2 predictor and a level 1 predictor, should explain? We talked about this with spur-of-the-moment PowerPoint demonstration last week. Do you remember that? Fun with PowerPoint? It works more reliably than the markers in this room. Let me get that out. Piles of variance and R-square. Yes, remember this? So generally speaking, cross-level interaction will reduce the random slope variance for its level 1 predictor if present in the model. For example, if I have a longitudinal model where the effect of time varies over level 2 people, then any cross-level interaction of a level 2 predictor with time will explain that random time slope variance. So the only terms in a model that are going to explain random slope variance have to have an interaction with the term that it's the slope for. So if this is linear time slope variance, only terms that interact with linear time can explain it. If this is quadratic time slope variance, only terms that interact with quadratic time can explain it. But what if I don't have a random slope for the level 1 predictor within the cross-level interaction? Remember what happened? It's residual. Yep. Because this is, the residual is where these random slope variances would have come from in the first place, and it's as if it's still buried in there. What source of variance? There's one more type that we haven't talked about, a purely level 1 interaction, like within something, let's say within person stress here by time. An interaction amongst two level 1 variables. Where do you think that goes? It's residual, yeah. It's the same principle as two level 2 variables reducing level 2 random intercept. Two level 1 variables reduce residual. All right, good. And then last but not least, random intercept for items. There was a long discussion about this in chapter 12 that may or may not have read carefully depending on your need, but when do you need to worry about having a random intercept for items? What kinds of research designs? It's the one that we looked at with the subjects in words, and it's also the subject of your homework 4. But more generally, when do we need to worry about having a random effect for items in addition to a random effect for people? When everybody responds to the same stimuli, items, words, toys, what have you, and they don't have to be fully crossed, by the way, but at least something in common. And what else is true? Any guesses? Okay, how about I give you an example? In your homework 4, there are 48 toys that all the kids in the study play with, and they all give a rating for how much they like the toy. And there are 4 different kinds of toys, educational or not, and fun or not. So there are 12 toys of each kind. In that kind of design, you need to worry about having a random intercept for items, because after including the things that differentiate items, fun or not, educational or not, there's still variability among items of the same kind. There's 12 fun, non-educational toys, there's 12 not fun, non-educational toys, and so forth. Now contrast that if I gave the subjects 4 toys, and I called one educational and one in each quadrant. Let's do it that way, right? 4 toys, 1 in each quadrant. After I put in what kind of toy it is, fun or educational or not, there is no more item variance to be explained. That's it. I've got 4 toys, which means there's 3 degrees of freedom. I could either put in a dummy code for which toy is which, that would do it, or I could put in a main effect of education, a main effect of fun, and the interaction. That's 3 degrees of freedom. That would do it too. So in that kind of design, the random intercept for items becomes unnecessary, redundant, once the item predictors are in the model. Whenever you have item variance that's going to be left over because there's more than one item of each kind, that's when you have to worry about a random intercept for items. So whether or not you fully explained why the items differ from each other with your design variables, that's an empirical question. The question is whether or not there's random intercept variance left over after you put in the things that you thought would create differences between items. So for that reason, if you're thinking of psychometric models where each item gets its own intercept and factor loading or its own threshold or difficulty and discrimination, in those instances we don't have a random intercept for items because each item gets its own effect. You use up as many degrees of freedom as you have differences between items and giving each item its own difficulty. So that's analogous to just having one item of each kind in that sense. If you don't allow differences between items in their fixed levels of difficulty, that's where you need a random intercept for items within psychometric models, which have a special name of explanatory latent trait models, right, Claire? She's like, I love these. They are so much fun. Right. I thought they were super cool. And unfortunately, I've never been able to get room for the lecture in which I get to talk about them. But someday I'll get back to that. I'd be happy to share more if anybody cares. But if not, then it's beside the point. So yes, so when you have repeated measures types of designs where there are differences between items above and beyond the reasons that you think there should be. There's more than one item of each kind. That's when you got to worry about it. All right, I think that's all the questions. Any questions about these questions? Okay. Do you want to look back at our, let's see, what do we want to do next? I'm open to suggestions. You want to do more PowerPointy things, or you want to go back to our example with clustered data? What do you feel like? Whoever gets to talk gets to choose. You want to go back to talking about poor kids doing badly at math? Or do you want to talk more generically in terms of slides and where stuff goes? PowerPoint? Okay, thank you for having an opinion. I know you guys care because you're here. That's how I know. And I'm sure people who care are listening on YouTube right now as well if they are sick. I got several emails from folks that they were under the weather. So hopefully everyone will feel better soon. So reviewing from last time, clustered data. New context, exact same set of problems and solutions. Whenever you have people nested within groups, naturally occurring or otherwise, but it happens a lot with naturally occurring groups like families, classes, schools, hospitals, and so forth, therapists, that kind of thing. So we have then, oh, by the way, do you remember the story I told you about fixed versus random? Let's talk about that for a second. When would you treat group as a fixed effect versus a random effect? Yes, fixed effect is like what are the differences between the groups? Like what is the difference between Sweden and Norway, right, in a country study? Or College of Arts and Sciences versus College of Education, if you're thinking about like colleges in a university study. When you care about the specific instance, that's a fixed effects model. When you want to know why they differ from each other and you want to be able to predict those differences with group level information, that's random. So the story I told you last time to illustrate when you might want a fixed effects model, even when you have a large number of groups, was the NCAA basketball tournament. Yeah, so my husband hasn't even put up his website for this year yet, and he got an email this morning from USA Today wanting to interview him. So how's that? Fixed effects models, this stuff, this not only gets you a paycheck, it can make you famous, apparently. USA Today, that's like for real. That's not even the UDK or anything. So fixed effect models, if you're interested in making inferences about the particular groups. Random effects models, if you're interested in predicting why the groups differ from each other with group level information. So the notation is exactly the same, except I'm switching up my subscripts. So here's my empty model. Interclass correlation is still the proportion of variance that's between, but now it's between groups in this story. We will not have an R matrix. If your interclass correlation is very small, or non-significant, too bad. You probably still need a multi-level model. Because what happens to it after you explain residual variance with level 1 predictors? Like we just talked about. What happens to your level 2 random intercept and thus your interclass correlation after you add level 1 predictors? It increases, yeah. So you could have an intraclass correlation that's 0 or nearly so in an empty model that becomes something sizable and significant later on because the residual variance has been reduced. They're yoked together. So there is no uniform value of intraclass correlation. That means you don't have to do a multi-level model. It depends on the intraclass correlation and the number of level 1 units, which together create a design effect. What is that thing? What's design effect mean? And I don't care if you use polite terms or impolite terms to describe it. What does design effect indicate? Yep, that's the effect of being screwed by clustered data in terms of your sample size, yes. It is the denominator for how your total sample size gets divided by that design effect to become your effective sample size. So best case scenario, your design effect is 1, meaning you've got as many people, as many observations as you think you do. Worst case, it could be all the way up to the number of level 2 units instead of level 1 units. So somewhere between the actual number of total observations that you have at level 1, children, for example, and children nested in schools, somewhere between that number and the number of schools you have, that's your effective sample size. So design effect is a way to try and anticipate what the effect of your clustering is going to be and then build that into your power process. Try and figure out how many schools you need. So even if your interclass correlation is very small, if you have a lot of level 1 observations per level 2 unit, you have a big design effect. All right, so then we start talking about how to center variables, right? So there's 2 choices. Predictors for clustered data, let's do that. So we have level 2 predictors in this story are between group things. They should always be centered using a number. Constant-based centering in a 2-level model, meaning make 0 mean something. Now, how to get them is trickier. If you have access to archival data from some other source that is a better, more complete representation of the characteristic of the group, use that. So for instance, as part of school's regular process of keeping records, they know what proportion of their kids get free and reduced lunch. That's something that they have to report on as a descriptive statistic for their school. In my example, I didn't have access to that information. I don't even know which school is which. This is de-identified data. So I had to aggregate. I had to average across the students from each school to get an indication of what the school's proportion of free and reduced lunch is. That is suboptimal. The only situation in which that is desirable is when you're pretty sure that you've got a representative sample for each of your groups, and then you can just go ahead and average the people, the responses within a group. But group level information should come from as correct a source as possible. It goes into the model centered so that 0 means something. Level 1 then. Level 1 in this case is people, and then you have your choices here. You can center at a variable, which is called group mean centering, and that is the term that you will see in papers that use this, where your original level 1 predictor has the group mean subtracted off of it, such that it becomes purely level 1, purely within, and that's the only kind of effect it can have in the model. Or you can take your original level 1 predictor and subtract a constant, or leave it uncentered, because you can subtract 0 as your constant, right? And in that case, you have not removed any variance of any kind. You've just shifted the scale. So the difference then in how you set up your model, these two choices, even though the variables are different at level 1, it's the level 2 effects that end up being different as a consequence. So I know we've done this type of thing before here, but let's do it again because practice makes perfect, right? So if I'm using variable-based centering, and I have my, let's call this within x equals my level 1 x minus my group mean x. Then it's purely level 1 in terms of its information, purely level 1 information. At level 2, I'll call my between x equals the level 2 x, let's go group mean x minus some constant so that 0 means something, purely level 2 between. So the fixed effect in the model then that you get back what does the coefficient mean for this within x variable that we've created this way? I'll give you choices. Here are your choices here. You can say within, smushed, between, or contextual. What's that one? That's within. What's that one? Between. It has to be because you've set up the variables to reflect only those sources of information. What happens if you forget this one? What are you assuming about the between effect? Is it the same or is it 0? In this one it would be 0. So between equals 0 if not there. Likewise, if you forget this one, what are you assuming about it? It's 0. Within equals, here, let's do this. Equals 0 if not there. There. Now, I like this version of things because it's harder to screw up. But within cluster data, people often want to know what the effect of the group is after controlling for the effect of the individual. That's the contextual effect, and this model doesn't give that to you. If I wanted to get the contextual effect out of this model, could I? How do I get it? An estimate statement, you got to ask for it. You remember? Between minus within, yep. So if you were writing your estimate statement, it would look like that. Within x minus 1, between x 1. That subtracts within x from between x. That's your contextual effect. Then you've got all three. So within is the effect of having relatively more or less than your group. So being like a big fish or a small fish in a little pond or a big pond, that kind of idea. Between is the effect of the size of the pond, the group characteristic. And the effect of the group characteristic after controlling for the individual is contextual. Gesundheit. Perfectly timed. Now, how does the story change if we change the way we've centered? So let's do it. constant-based centering. And I'm just going to call that level 1x. Is it purely level 1 within? Nope, it's both. It's smushed together. Both level 1 within, make that W, and level 2 between. So let's do the first part of these things here. This effect of level 1x in the model. So long as I have this between x in there too, is it still within? Yeah, this is a tricky one. So long as this other one's in here, it is. Because you've controlled statistically for the between part by including this variable. So its unique effect in the model becomes the level 1 part. This one, this is the one that switches. So even though it's the level 1 variable that we changed, the level 1 effect stays the same. Even though the level 2 variable is the same, its effect changes, and it changes to contextual. So that means we are missing, of the 3, we're missing between. And if I want to get it back, add them together. So it would be level 1 x, and this between x gives me the between. That's why I tend not to use between as a label. I tend to use like grand mean x or something like that, because sometimes it will mean between and sometimes it will mean contextual based on how you've set up your model. So under this framework, you are assuming the contextual effect is 0 if it's not there. But what that then means about the within is that it becomes smushed equals between if no contextual. And that's the problem one. That's when you put in a level 1 predictor that has both level 1 and level 2 variance. Its one single effect has to be both of them, which means you're assuming no contextual effect or no difference of the within and between effects. Now this way is more complicated, right? Can we all agree with that? Keeping track of what this means? Now the predictor that I have in my story is a binary variable. It's called free and reduced lunch, and 0 equals paid lunch, and 1 equals some kind of free or reduced. Am I going to group mean center that? Could I? SAS will let me, I'm quite certain. So let's say that I have a school where the school mean free and reduced lunch equals 0.3. That is the mean. So anybody who had a 0 now gets what if I center at 0.3? Negative 0.3. And if I had a 1, what do they get? Yeah, 0.7. So if you look at those coefficients, they're still 1 unit apart, right? In terms of the effect of this variable, it could be 0 and 1, or it could be 242 and 243, right? It's a 1 unit change, doesn't matter. Now, when does this, well, I'll give you say, when does this make me squishy? This is the what would Lesa do portion of the program. In what other kinds of effects would this constellation make me squishy? I've talked about this before in the context of effects coding. Like if I had done plus or minus 1, for instance, or plus or minus 0.5. I talked about it with reference to groups. I don't like effects coding for groups in most situations. Because, what does 0 mean? 0 means everything with respect to the intercept, right? So if I have my intercept for my predicted math score, how does that apply to this variable? It doesn't. What if I want to interact this variable with other things? The interacting variables are conditional on when this is 0. When is this 0, and according to this coding scheme? Never. So it's not wrong, but it's weird. So for binary variables, if you leave them alone, just leave them alone, because 0 already means something, that's perfectly fine. But you have to keep in mind then what you're going to get back is the within effect and then the contextual effect rather than between. So whenever you have a binary variable that you don't want to center at a variable and have it make no sense, you're going to have to learn how to live in this within smushed contextual world correctly. And that's what this, the example that we're working with is teaching, or trying to teach anyway. That's why I did it that way. Questions? So we did that. This is group mean centering. We did that. We did that, did that, did that, did that. Contextual effects, think we did that, we did that. Then this. This is the same slide that you've seen before in a new context, and what we had our quiz over today. Slide 25. Fixed effects of level 2 predictors by themselves. Their main effects reduce level 2 random intercept variance. Level 2 interactions also reduce random intercept variance. If you have a cross-level interaction, if the level 1 predictor is random, that cross-level interaction will reduce that random slope variance. If the level 1 predictor is not random, it will reduce the residual instead, and the level 1 predictor would be called systematically varying. Level 1 predictors then, a main effect of a level 1 predictor should reduce residual variance, and interactions among level 1 predictors should also reduce residual variance. What happens at level 2 then depends on what kind of variance it has. If the level 1 predictor does have level 2 variance in it, its intraclass correlation is greater than 0, it will reduce the random intercept. If it does not, then the random intercept goes up instead. And the reason that it goes up is right here. The model is trying to estimate the true random intercept variance by correcting the observed random intercept variance for what it thinks is the contribution of chance, and it operationalizes chance as residual variance divided by the level 1 n. So to the extent that that residual variance goes down, the true random intercept variance will look like it goes up. All right, before we get into interactions then, let's go back and talk about poor kids. Yes. Getting kids lunch reduces their math scores. Story at 11 or something. Yes, I know that sounds ridiculous, but just keep in mind that even in longitudinal data, causality comes from design. So long as you've observed these things at the same time, we can say nothing about causality. These things are associated. So we have 13,000 and some odd kids from 94 schools. I am working with a single variable as a predictor here in predicting math. It's whether or not a kid gets free and reduced lunch. We looked at an empty model to describe the variation in math scores. So if I add a random intercept variance for school, it accounts for 15% of the total variation in math. I wouldn't say accounts for in the sense of explains. I would say it's attributable to. We don't know why it is that some schools differ in how their kids do in math. We just know that it is. 15% of the variability in math has to do with which school you go to, and that is significantly greater than 0. There's my model comparison. If I do a design effect calculation given the add intraclass correlation and the number of students within a school on average, the design effect is a whopping 42. And I can try to describe what it means to have an intraclass correlation of 0.15 in terms of the range of the original variable. Math scores at the individual level varied from 0 to 83. Mean math scores at the school are predicted to vary from 35 to 61 in 95% of the schools. So that's a pretty big difference. We then added free and reduced lunch as a dummy code into the level 1 model. It's first added as a fixed effect here. So all schools get the same difference between kids who pay for lunch and those who don't. And we had interpreted that coefficient, a 9-point disadvantage for those who get some kind of lunch reduction. And I had asked you, should I write it up and turn it in, or have I committed a cardinal sin? Bedtime stories with statisticians. It's smushed, indeed. I have a level 1 predictor in my model with nothing in level 2. What I am saying is that it doesn't matter what kind of school you go to. It only matters about your lunch status. There's no extra effect of going to a school where there's lots of poor kids. That's a testable hypothesis. So this is an example of a variable that has both level 1 and level 2 variation in it. The proportion of kids who get free lunch ranged from 0 to 80% across schools when I looked at the descriptive data. That indicates that this has school level variance in it, even though it's just a binary variable. And as expected, given that it's level 1 predictor, it did reduce residual variance, 5% of the residual. So of the 85% of the variability in math that was due to children, 5% of that 85% has to do with free lunch status. But then, surprisingly, I also got a 40% reduction in the 15% of the variance that was due to school. The between school variance in free and reduced lunch that is buried in this variable, it reduced the random intercept at level 2 by 40%. We then fixed it by adding the school level analog, free and reduced lunch school mean, which is a proportion that ranges from 0 to 0.8, with a mean of about 0.3, and so that's what I used as my centering constant. By the way, if I were doing this model for real and not for pedagogical purposes, I never would have started with the smushed model. That is purely to demonstrate what happens. When I would talk about next we added free and reduced lunch to the model, I would add them both at the same time. I would add the variable at every level at which it belongs, unless you have some very specific reason to delay that to make a story out of it. This would be my starting model. So now, we have introduced a level 2 predictor that has purely level 2 between variance. My level 1 predictor is now the unique effect of its level 1 variance, so this is purely within. So it's very close to what it was before. Before it was minus 9.43, and now it's minus 9.17. So you may say to yourself, what's the big deal? It's off in the second decimal place. We have 13,000 students, and only 100 and some schools. That's why that number is very, very close to the within effect. There's a lot more information there. The problem with smushing is not what it does to the within effect most of the time, it's what it does to the between effect. This level 2 predictor is the contextual effect. It is the test of whether or not you're allowed to smush. If smushing is fine, it will be 0. Within plus contextual, the minus 9 plus the minus 16 is the minus 26, that is the full between school effect. Do you remember why these numbers are so ginormous? Have you seen a slope of minus 26 any time in your lifetime? It's pretty big, right? Remember why? Yeah, a unit, right? This is the change in y per unit change in x. A unit is going from 0 to 1, meaning no students in your school with free lunch, to everybody gets free lunch. We don't even have a school in our sample where everybody gets free lunch. So to make sense of this, what I would do is divide it by 10. So for every 10% more poor kids at your school, Gesundheit, everybody at your school has lower math by minus 2.6. The whole school. Schools with more poor kids do worse. Specifically, for every 10% more poor kids, scores on average go down by 2.6. That's the between school effect. If I want to know what it is after controlling for individual free and reduced lunch status, that's the contextual effect. So after controlling for individual free and reduced lunch, the extra effect of going to a poor school is 1.6 points per 10% more poor kids. Yes? Because I'm bad at math usually, and I can move a decimal over off the top of my head, but I can't do any other transformations reliably. No, I'm serious. That's why. And I could have started by rescaling it, but then it wouldn't be the contextual effect exactly, like I want it to make the point of what those things mean. So, but yeah. So the between school effect is minus 26. After controlling for the individual effect, it reduces to minus 16. But it still means that if you are fine, your parents have lots of money, you are still hurt by going to a poor school. So how much are you hurt due to your individual